This is the Chapter 5 Functional Groups, Acids and Esters commentary. Should probably change that. Yeah. So Part 2 commentary. So again, Part 2 commentary. So now we're going to focus on various types of carboxylic acid derivatives, such as acid halides, and we'll talk about additional reactions involving these acid halides and esters, along with a few other things. So, before we begin, let's go ahead and first take a look at this reaction right here. So, in the upper left-hand corner, we have the traditional esterification. So here we have a carboxylic acid. Its name is butanoic acid. And then we have a alcohol. This is 1-propanol. And what's going to happen is, just reviewing our traditional esterification, using an acid catalyst and having an alcohol. Let me go ahead and duplicate both of these molecules. That way it'll make it easier. Okay. There we go. So what's going to happen is these two molecules are going to form a brand new ester. There we go. So the hydrogen, oxygen, and hydrogen from this other alcohol molecule are going to go ahead and form a brand new water molecule. And the leftover oxygen and then hydrogen will come together and form a brand new ester bond. So here is our brand new ester. Its proper name is propyl, and then butanoate. So just a quick review. Now, this is a reversible reaction, because just as soon as this product forms, the same or a nearby water molecule can come along and cause a reverse reaction, which is why we have a reverse arrow showing this arrow. When it does that, it creates the original reactants. So this is a common problem found in industrial chemistry. If we want to make a desired ester product, let's say we want to make a new ester flavoring, for example, we need to make sure that we have a permanent product. However, in this type of ester reaction, it's considered a reversible reaction, because just as soon as the product forms, a reverse reaction can immediately occur, resulting in the original reactants. Now, to create a desired permanent product, we have another type of esterification that we can go ahead and use. This requires we first create what's called a acid halide. So notice it has a carbonyl group. However, instead of an oxygen, we have a chlorine that's directly attached to the carbonyl carbon. So this is called a acid halide. This is the category, an acid halide. This is often referred to as a carboxylic acid derivative. since we've taken off the alcohol group and put on a halogen. This is the halogen that we put on, a chlorine. So this is often referred to, especially in the slides, as a acid chloride. An acid chloride. As far as naming goes, when it comes to naming these acid halides, we're going to go ahead and identify the parent. We then drop the E of the parent and add the suffix oil. Oil. So in this example right here, the name of this one would be, let's see, the parent, carbon 1, 2, 3, 4. So that's a butane. However, I'm going to drop the E and I'm going to add in oil. So this is butan oil. We then need to go ahead and add a space, or a couple spaces in between, and then add in the rest of the name. It's a halogen, so we take the halogen name, such as chlorine, and we're going to drop the suffix part of chlorine and change it to ide. So it's no longer chlorine, it's chloride. So you go ahead and you add the halogen name, changing the suffix to ide. Ide. Let's go ahead and investigate this a little bit further, and I'm just going to go ahead and make up a quick example before I show you this whole non-reversible reaction. So in this case right here, and I'm going to go ahead and change this. I'll change this oxygen we see here, and I'll add in my hydrogen. So originally it was, in this case right here, whoops, add in my oxygen. There we go. Then I'll edit this, add in a hydrogen. There. One more time. Add in the oxygen. Come on. Edit the atom. Change this to hydrogen. So here we have the original acid, and I'm going to go ahead and drop the oxygen and replace it with a halogen. I think I'll change this one. Instead of a chloride, I'll change it to an F for fluoride. So now the name is going to be, let's see, we start at carbon 1. Here's carbon 1, then carbon 2, carbon 3. So instead of propanoic acid, it would be propan oil fluoride. Notice how I changed the suffix of "ene" as well and added IDE. Alright, so those are practice names, so you can go through those, but the purpose of having an acid chloride is when I mix it with an alcohol, it creates a non-reversible product. So we call these non-reversible reactions. So let me go ahead and create another one, and I'll scroll over to the side here. Oops. So let me go ahead and go here. And then we go ahead and we have, I'll just remove the plus for right now. So what'll happen is the chlorine and the hydrogen will come together, forming another product, an HCl. HCl. You then remove the chlorine, and then you go ahead and we're going to attach the oxygen. So now we have our ester again. That'll be a really long chain. Let me bring this over a bit. Now we have our ester, and this is a permanent ester. A permanent ester. So notice we created again propylbutanoate, but now this is permanent. And then we have our leftover side product, an HCl. So let's go straight to our slides now. Here we have this acid halide, and it could be fluorine, chlorine, bromine, or iodine. Because it's a chlorine, the slides are more specific. Because it's a chlorine, we call this, instead of an acid halide, we call it an acid chloride. Here we have the alcohol. Notice the hydrogen and chlorine, again, they come off, forming HCl. The leftover oxygen from the original alcohol will then go ahead and bond to this carbonyl group, forming our ester. And again, this is a non-reversible ester product. Here's another example down here. Chlorine, hydrogen, forming the HCl. And then we have the leftover oxygen and carbon coming together, forming our ester product. Again, reviewing the name. So the class in this case is acid chloride. As far as naming it, if you recall, it was originally an OH that was attached. And we don't talk about how we form these acid chlorides. We just say that they exist. But originally there was an OH attached, which is a acid. But we replaced the OH with a chlorine. So it's a acid chloride. It's a bit redundant, so let's go ahead and move on. When you have a chloride attached, then the proper name is ethane, because that's the parent. But we drop the E and add in oil. Oil, O-Y-L. We then put a space in between, and then we put the name of the halogen. And the name of the halogen is chloride. In green, we have the common name, acetyl chloride. But you'll be responsible for giving the proper UPAC name. I can give you various molecules, and you should be able to predict what the UPAC name is going to be, or sketch it from the UPAC name. Here we have carbon 1, carbon 2, 2-methyl, and then the parent is a butane, so butanoyl chloride. In this case over here we have a aromatic benzene, and originally it was benzoic acid, but substituting the OH with a Cl, it's now benzoyl chloride. Careful, I could make this more difficult on you. If I wanted to, I could add in another halogen branch. So let's say, for argument's sake, I added in a fluorine, and it's on carbon 3. Then the new name for this one would be 3-fluoro-2-methylbutanoyl chloride. Keep in mind, it can only be an acid chloride if the chlorine is directly attached to the carbon. Now, short of something like this, I'm not going to get any trickier. Even more, if I do give you a extra branch or a branch derivative, such as a halogen or an alcohol, I will make sure that they are only prefix related branches or substituents or branch derivatives. Bottom line is they'll be prefixes. So I'm not going to give you multiple suffixes along with these. Let's go ahead and move on. Here is another way of creating a permanent ester. Now, originally we had a carboxylic acid. So I'm just going to write over this one. So pretend like this other part isn't here, and we just had this. What we've done is we've basically added two acids together. We don't tell you how we did this, just accept that this happened at some previous attempt. And we've added two acids together. So both of these acids are sharing this particular alcohol, originally alcohol oxygen. So because there are two acids that were put together, we call this a carboxylic acid anhydride. Now, these can be very difficult in their own. So if I ever give you a question on carboxylic acid anhydrides, this is the only example I would give you. And essentially what I would do is I would literally cut and paste these starting reactants and ask you to predict the products. I'm not going to get crazy on this. I'm not going to have you learn the naming schemes for this. Simply predict the products for this example only. You can look for the pattern that I'm about to show you, or you can just sit there and memorize the products. Why am I doing this? Because we have so much other stuff to conquer, and it's one way that I can make it a little bit easier. So essentially what happens is we take a look at our demo of a carboxylic acid anhydride. This is going to break apart, and what's going to happen is this portion right here is going to combine with this particular hydrogen and is going to form a brand new carboxylic acid. The remaining parts of each of the two substances, the carbonyl group and the previous alcohol, it's actually called an alkoxy. The previous alcohol will combine, forming a brand new ester. Here is another example. So again, this anhydride will break apart. This oxygen will combine with this hydrogen, forming a brand new acid. And then the remaining part, the carbon from the carbonyl group on this acetic anhydride will combine with the leftover oxygen from the previous alcohol, aka phenol, forming this ester right here. Let's go ahead and move on. Polyesters. So, in this example right here, we have a molecule with acids on each side of the parent molecule. So on this parent, we have acids on each side. Notice, for our alcohol, we have alcohol functional groups on each side of the parent as well. So what happens is when you have a whole bunch of these acids and glycols inside a solution, basically, and I'm going to summarize it like this, where I have the acids, and I'm going to show OH. Well, I'll take that back. I'm going to go ahead and show a terephthalic acid. So here I have the CO, OH, CO, OH, And then here I have the ethanol. Basically what's going to happen is you're going to have back-to-back esters that are forming. So in this case, this is going to come down here, and you'll have back-to-back esters. Because I'm short on time, I'll go ahead and I'll just draw the line structure. So here's our ester. There's our next carbon. I'll just summarize it like this. This is not a proper way of writing it, but due to time constraints, I'm just going to simplify it. We then have our previous alcohol that esterified with it. And as you can see, it just keeps on going. So think of these as links in a growing chain that form over and over and over. In parentheses, we put this as a repeating unit, and it basically just keeps on getting bigger and bigger. Because we have multiple esters that form, we cleverly call this a polyester. These are very strong fibers used to create these very ugly polyester pants. Now you know where the name came from. You are expected to memorize and understand the general idea. I am not, however, testing you on actual reactions. Just know the overall reaction theory, know the name of the reaction.